Hi, I'm Stefan.
And my name is David.
Together we present to you SLIM, a new method for self-supervised LiDAR scene flow and motion segmentation. Using a depth sensor, such as a LiDAR sensor, two consecutive point clouds PT and PT+1 are recorded. 3D scene flow then refers to the 3D vector field F, assigning each point in the first point cloud PT a displacement vector pointing to its corresponding position in PT+1. This flow vector represents the underlying motion of the object. Actual one-to-one correspondences between point clouds usually don't exist. Scene flow allows us to reason about motion in a scene, which is critical for safe autonomous driving. From the perspective of a moving sensor, there are two different sources of motion in a scene. The first is caused by the sensor's ego motion and is consistent across all of the static background points. The second source of motion stems from other moving actors, whose motion profile stands out from the background. Classifying the points in the point cloud into these two categories, moving and static, is called motion segmentation. 3D scene flow in combination with motion segmentation allows us to reason about motion in a scene and safely interact with other moving actors. However, it is very expensive to label by hand, so we investigate self-supervised learning. This is challenging, especially at larger distances, where measurements become very sparse, which leads to noisy flow estimates. But most points of autonomous driving scenarios follow the rigid ego motion transformation, allowing for aggregation and smoothing on static points. Self-supervised motion segmentation enables us to aggregate and thus improve scene flow estimation in a scene. I will now explain the core idea behind our approach. We are interested in the scene flow going from the first, colored point cloud to the second, gray point cloud. There are both static and moving objects present in this scene. The initial training phase produces a rough scene flow estimate between the two point clouds. Early in the training, the motion segmentation output is very noisy, and the aggregation we perform does not yet discriminate well between moving and static objects. The resulting flow for the moving objects is therefore incorrect. However, applying this aggregated flow to the first point cloud and comparing the endpoints to the second point cloud hints to which points are actually moving. We used approximate error estimates to extract a training signal for our network to learn motion segmentation, teaching the network to treat the two types of motion separately in future training iterations. When static and moving objects have been successfully identified by the network can aggregate flow estimates for the static scene elements more accurately. This improves the training signal for the motion segmentation. Overall, this self-improving motion segmentation regularizes the training, ultimately also improving the scene flow predictions for moving objects. To summarize the main contributions of our work, our method is the first to perform self-supervised motion segmentation, as demonstrated on the right. The usage of this learned motion segmentation enables aggregation of scene flow and thus improves scene flow predictions, as we demonstrate in experiments. Also, we introduce a new network architecture capable of handling more points than previous methods for scene flow estimation, leading to improved performance with respect to the current state of the art. Next, we discuss our network architecture and the losses of our framework. First, the input point clouds PT and PT+1 are voxelized into vertical virtual pillars and separately encoded into a bird's-eye view pseudo-image using the pillar feature net, or PFN, with shared weights. The resulting sparsely populated pillar feature maps are then processed by the backbone. Our backbone is inspired by Raft, which was developed to predict dense optical flow on images. Its core component is an update block acting recursively on a hidden state and a flow prediction, producing a more refined and accurate flow with every iteration. Inside the update block, a correlation volume is constructed from the two independently encoded pillar feature maps. Iteratively, the previous flow predictions are used to look up correlation values and thus guide the flow to a more accurately matching region. We adapt Raft to not only handle flow predictions, but also iteratively update two additional logits. The first logit map, LCLS, is used for the actual motion segmentation. The second logit, LWGT, allows the network to signal its confidence in a flow estimate. Both logits are used by the network to steer the aggregation process and thus improve accuracy on static scene elements. The differentiable Kabsch algorithm is used to perform the weighted aggregation of the points identified as static by the network, giving us a single ego motion transform for the static scene elements, in addition to motion segmentation and the raw flow predictions.
After constructing the network we use for processing the 2 point clouds, we need to train those 3 outputs in a self-supervised manner. In order to do so, we make use of a combination of in total 3 losses. The first is the nearest neighbor loss. It applies forward flow prediction to the input point cloud and compares the distances of the endpoints to the points of the second point cloud. We opt for directly minimizing this nearest neighbor distance. Because we also have the transform from the Kabsch algorithm, we use it to produce rigid flow and apply the nearest neighbor loss to this rigid flow component as well. Our initial experiments showed that this makes the training more stable. The second loss we made use of is the rigid cycle consistency loss. In addition to the forward inference, we make a time-reversed inference pass during training. Doing this allows us to use both the forward and time-reversed rigid transforms, which need to be consistent with each other. This loss component takes care of that by applying to every point the forward and then reversed ego motion prediction and minimizing the distance to the starting position. The third and most important loss is the artificial labels loss. In order to train the motion segmentation output of our network, we need a self-supervised mechanism to train this network head. We do this by comparing the nearest neighbor distances of the raw flow prediction with those from the rigid flow prediction. When the rigid flow prediction has a larger nearest neighbor distance, then the point is considered moving, like in the upper right case. In the other cases, the rigid flow has actually a lower nearest neighbor distance. This signals the network a static point. In order to backpropagate this information into the network, we use a simple softmax cross entropy loss and substitute the ground truth classes with these self-supervised artificial labels. For our experiments, we made use of different datasets. In this presentation, we will only focus on 2 of them, the Kitty stereo flow and the NuScenes dataset. The Kitty stereo flow is heavily post-processed as it combines LiDAR, stereo depth, and RGB optical flow into a scene flow annotation of the stereo depth point cloud. The metric used to evaluate the performance is the average endpoint error. As the dataset is small and therefore can only be used for validation purposes, we also processed the raw LiDAR point clouds from the Kitty dataset in order to train our method. For a more realistic flow scenario, we opted for the NuScenes dataset. Its data allowed us to annotate the point cloud with scene flow through the usage of object bounding boxes, which were densely annotated across time. It is important to note that in contrast to the Kitty stereo flow dataset, which only has a field of view focused on the street in front of the car, the NuScenes dataset records a full 360 degrees field of view and has therefore a much higher point count of static scene elements, roughly 95%. Therefore, we don't report the raw average endpoint error, but a separate average error for static and moving points, as well as a 50-50 combination of both scores in order to balance the importance of static and moving flow accuracy. The first set of experiments on Kitty shows the importance of being able to train on larger point clouds. We compare here 2 state-of-the-art methods for self-supervised scene flow against ours. Both baseline methods can only be trained using not more than 8,000 points due to the runtime and memory constraints. However, the inference can be done on the complete point clouds. Although the complete point clouds potentially hold more information for a more accurate flow prediction, both baseline methods actually suffer under the increased point density. We contribute this to the domain shift with respect to the changed density. Our method can avoid the domain shift by training on the same point density as during evaluation. The scores of our method show that not only generalizes our chosen network architecture better to the scene flow task, but also demonstrates the importance of being able to train on the full-sized point clouds and thus avoiding a domain shift during inference. In the second set of experiments, trained and evaluated with the NuScenes dataset, we investigate the effect of our main contribution, the motion segmentation and flow aggregation. Without this ingredient, our network performs significantly worse. To our surprise, the static scene flow seems worse than the flow of moving objects. As explained during our motivation, we contribute this to the large number of static points observed in a large distance to the ego vehicle, resulting in a bad performance of the nearest neighbor signal in these very sparse regions. The motion segmentation and aggregation helps to produce very accurate static scene flow. In addition, the added regularization through our losses and the motion segmentation task helps the network to also better perform on the moving objects as well. We also evaluated the baseline methods on the NuScenes dataset. With NuScenes being much sparser, those methods really suffer and are therefore not suited for this task. PostFlow does show a promising static average endpoint error. However, the method is specifically designed to first estimate the ego motion, correct for it, and then predict the non-rigid motion component. Our experiments indicate that this seems to make the flow prediction for moving objects even harder, as the resulting average error is worse than simply predicting a flow of 0 for every point, with those scores noted in the top row. In this short video, you see our network performance on the raw Kitty LiDAR point clouds, on which we also trained self-supervised, so without the use of any labeling. The left part shows the scene flow, the right part is the classification output for the motion segmentation task. We observed that the segmentation of the bicycle and the car work quite well, and that the scene flow estimates realistic flow for those two objects. The rest of the scene makes use of the rigid transform and produces a very coherent flow field, based on the indication of the motion segmentation output. To summarize our work, we trained very successfully a new network architecture for 3D scene flow without the need for prior downsampling of the point clouds. Our core idea of using flow aggregation to identify motion and in turn train and improve the motion segmentation demonstrates another boost to the scene flow prediction task. For more detailed experimental analysis and fine-grained ablation studies, please refer to our paper and supplementary material. Thank you for your attention.